This is Catherine Nightingale of Chattanooga State Community College. This is video 2 for section 11.6 of Calculus 3, Math 2110. The topic is graphing quadratic surfaces in 3 dimensions. Let's start by talking about what a quadratic surface is. It's a graph in space of a second degree equation in x, y, and z. So second degree meaning that at least one of x, y, and z are squared. To graph a quadratic surface, we need to figure out what the cross sections look like, which are the sections of the surface parallel to a coordinate plane. So to graph, figure out the shape of each cross section, and the way we do this is let one variable at a time equal a constant. So we'll walk through 3 examples in this video of graphing quadratic surfaces. The first example is x squared plus y squared equals z. So it's a quadratic surface because the highest degree of the equation is 2. So we have it set up so we will get 3 different cross sections. The first one, when x is constant, what I'd like to do is let x equal 0. Then what I have is z equals y squared, so I can graph that 2-dimensionally on the yz axis, or yz plane, and I get a parabola. So that's what the cross sections will look like. So this is a parabola, and it will shift up for different values of x. Now, the reason that it would only shift up is because x is squared, so it will always be positive, so you'd always be shifting up. You would never go below the y-axis. Okay, now let's focus on the next cross section when y is constant. Let's let y equal 0, and then we get the equation z equals x squared, which is also a parabola, so I'll set up my xz plane and go ahead and graph that parabola. Now this one will also shift up for different values of y. Again, the reason it only shifts up is because y is squared, so you'd always be adding a positive number, so it will never go below the x-axis. Now our third cross section, I'm not going to try to draw it, I'm going to look at the different possibilities. So the first one, when z is 0, x and y have to be 0, because they're both squared. So I couldn't be subtracting something from something else to get 0. I'm only adding positive numbers. So I have the graph going through the origin. Okay, the next thing to notice is z can never be negative. This is because it equals x squared plus y squared, which will always be a positive or 0. So z never goes into the negative part of the graph. Okay, now the third possibility is when z is positive. So for positive z, the curve x squared plus y squared equals a positive number, and that would be a circle parallel to the xy plane. The reason it's parallel to the xy plane is because it's x squared plus y squared. Those are the 2 variables that are present. Now we want to put all of these together. So we put our 3-dimensional axes, x-axis, y-axis, and z-axis. I start by drawing my parabola in the yz plane. I also have a parabola in the xz plane. And then parallel to the xy plane, I have a circle. And so putting all that together, let me just shape up this graph a little bit. I'm going to have this cup-looking thing, which is called an elliptical paraboloid because it involves an ellipse and parabolas for two of the cross sections. Now, in this case, we have an exact circle, but a circle is a special form of an ellipse, so it's still an elliptical paraboloid. Now, what I'd like to show you is how to use some technology to do your 3D graphs. What I'm going to use is Wolfram Alpha, which you can get to by going to, if you just Google Wolfram Alpha, it will come up with this website. And what I'm going to do is I'm just going to type in plot and then my equation, z equals x squared plus y squared. And then once I press the equals key, it plots the graph for me. So the only thing that's different about plotting this by hand is they usually rotate the x and y axes. There's your origin in the middle of the graph, and then you have your x-axis is coming out to the right, your y-axis is coming down. So they basically rotate it from what you're used to drawing with in the 3D graph. So while you're doing your homework, always check to see if you're getting the correct figure by checking in Wolfram Alpha, or if you have a TI-89 or TI-Nspire, those can both handle three-dimensional graphing as well. Our next example is x squared minus y squared equals z. Now this may take a little review from pre-calculus on hyperbolas. So we'll go over that when we get to our third cross section. The first one we want to look at is when x is constant. So I'm going to let x equal 0. Then z equals negative y squared. So I just have an upside down parabola in the yz plane. Now, if I pick a different constant for x, it will shift the graph up because x squared will always be positive. So this parabola shifts up for different values of x. Our next cross section will be when y is constant. So I'm going to start by letting y equal 0, then z equals x squared, which is a right side up parabola. So I go ahead and graph that in the xz plane. And if y were a different constant, you'd be subtracting a positive number, and so it would shift the graph down. So it shifts down for different y values. Okay, now our last cross section is when z is constant. And I have a couple situations. If z equals 0, then x and y are 0. So the graph goes through the origin. You could also have x squared equals y squared. So you could have the lines x equals plus or minus y, or y equals plus or minus x. But the main point is we know that the graph goes through the origin. Okay, our next possibility is when z is a constant c, then we get x squared minus y squared equals a constant, and that's a hyperbola. So it may have been a while since you've dealt with hyperbolas, so let's go ahead and review. A hyperbola is of the form x squared over a squared minus y squared over b squared equals 1. And when you have that, you have asymptotes that are defined by y equals b over ax and y equals negative b over ax. And then your hyperbola follows these asymptotes. It goes through the point a and negative a on the x-axis and approaches those asymptotes. Now, if the y squared came first minus the x squared, then my hyperbola would go along the y-axis, so it would go up and down instead of left and right. So that brings us back to our cross sections. We have two possibilities, positive z or negative z. So for positive z, we're going to get x squared minus y squared. So I'll have a hyperbola going like that. For negative z, to get into the standard form of a parabola, I'd have to divide by that negative number, and so it would become y squared minus x squared. The signs would switch. And so my hyperbola is going to open upward and downward. Okay, now I want to put all of this together. So I have my x, y, and z axes. I'll start with the z equals negative y squared. Or actually, let's start with z equals x squared. So I have z equals x squared on the xz plane. And remember that can shift down for different values of y. So I have different parabolas as I move my y value. Okay, now I have z equals negative y squared on the yz plane. So I have my parabola opening downwards, and for different values of x that will shift up. Okay, now I put this together and I end up with this shape that looks like a saddle or a Pringle potato chip, basically. These are often called saddle-shaped graphs. And then my last cross section was hyperbolas, so I can go ahead and draw those in. But basically that just shows the basic shape. So we still have this saddle shape for our overall graph. And what this is called is a hyperbolic paraboloid, because it involves hyperbolas and it involves parabolas. So a hyperbolic paraboloid is always that saddle shape. In Wolfram Alpha, you can go ahead and put that in, right, plot z equals x squared minus y squared. It gives you the saddle shape, and remember your x and y axes are reversed from what you're used to seeing when you're graphing in 3 dimensions. So there's your saddle shape graph. The last example that we'll go through in this video is 4x squared plus 9z squared equals 9y squared. So we have a few different situations. When x is constant, let's start by letting x equal 0. Then we have 9z squared equals 9y squared. So z would equal plus or minus y. Let's go ahead and graph that on our yz plane. We have two crossing lines, z equals y, z equals negative y. We also have another situation when x equals plus or minus 1, or basically some non-zero constant. I would get 4 plus 9z squared equals 9y squared. Now if I get this into a form that I know the shape of, I would have 4 equals 9y squared minus 9z squared. So this will be a hyperbola because I have a positive squared term minus a squared term. So this would be a hyperbola opening left and right because the y part is the positive part. So I'd get a hyperbola like that. And I would just get different hyperbolas for different values of x. Okay, now let's let y equal 0. Then I would have the point 0, 0, 0. Or I could find some relationship between the x and the z. But the point is that I know my graph goes through the origin now. When y equals plus or minus 1, I would get 4x squared plus 9z squared equals 9. And we know that this is the equation of an ellipse parallel to the xz plane. We know it's parallel to the xz plane because it has the x and the z in it and no y. The last cross section, when z is a constant, will be similar to when x was a constant. So when z equals 0, I get 4x squared equals 9y squared. So I could find the relationship y equals plus or minus 2/3 x. So I get two crossing lines. And when z is a non-zero constant, let's use plus or minus 1 because it's easy to graph. I get 4x squared plus 9 equals 9y squared. Get the constant by itself. 9 equals 9y squared minus 4x squared. And I have a hyperbola opening up and down because it will open in the direction of positive y and negative y, because the positive term in my hyperbola equation is the y term. Okay, so I have up and down. Okay, now we need to put all of this together. We'll start with our ellipses. So our ellipses are parallel to the xz plane. And then let's graph our crossing lines and our hyperbolas. And now just put it all together. And you end up with this shape that expands both directions along the y-axis. And it's known as an elliptical cone because you have a cone that has an ellipse as the shape of the bell part. Let's go ahead and graph this in Wolfram alpha. Here's our equation, 4x squared plus 9z squared equals 9y squared. And notice that they kind of rotated around. So your x-axis is going up and your z and y-axes are along the floor of the graph you're looking at. So the y-axis is what the cone opens around. So that does it for our examples. The last thing I want to talk about is the 6 types of common quadratic surfaces. You should kind of become familiar with these. They're in your book and in your notes. So we'll just go through them very quickly. You have an ellipsoid when you have all 3 squared terms added together equaling 1. So you end up with this egg shape. You have an elliptical paraboloid. We graphed an example of that. That's where 2 of your terms are squared and added together. to equal the third term, which is not squared. Elliptical cone, where you have two of your terms squared and added together equaling the third term squared. Hyperboloid of one sheet, where you have one of your variables squared added to another one squared, and then you subtract the third squared term, and all of that equals a constant. You have the hyperboloid of two sheets, where one of your terms is squared and positive, and you're subtracting the other two squared terms. And you have your hyperbolic paraboloid. And we did an example of this one, where you have a squared term minus a squared term equals a non-squared term. Those are your 6 common quadratic surfaces, and you can graph all 6 of them by looking at the cross sections, as we did in the examples. If you have any questions, we'll address them in class, and make sure as you're doing your homework for this section, you think about the cross sections as you're graphing.